Just like an adjacency matrix, there are two different ways of expressing the edges, the relationships between our vertices. Okay, now let's compare them. So here's kind of an intimidating slide that talks about the big O notation between adjacency lists and adjacency matrices for various operations. So first, a couple of things I should explain. V and E. So V is the number of vertices, E is the number of edges. So if we think about the storage, how much space they take up compared to one another, if we look at an adjacency matrix, you can see we're looking at big O of V squared, where V is the number of vertices. And that makes sense because it's a two-dimensional structure. If we add a new vertex, it means not only just adding one slot in, it means actually adding an entire row and an entire column to our matrix. Compare that with an adjacency list, it really only grows at the rate of the number of vertices and edges. So I think that makes sense, right? All we have to store here, really, the size is governed, or if we go back to this example, same thing in adjacency list. The size of it, the amount of storage, is determined by how many edges, how many connections we have. But if we go to our matrix, it doesn't matter how many connections there are, it matters how many vertices. So we could have 100 more vertices, or let's be more conservative, let's say 9 more vertices, and they might not have very many connections. They could only have one each, one edge each. Well, we're still going to have to add 9 rows down here or up here and 9 columns, and that's a lot of space. So if your data is sparse, if you don't have a lot of connections, a lot of edges, maybe don't use a matrix. So you can use this slide as a reference, but here's a breakdown of some of the key points. So an adjacency list, as we've already talked about, can take up less space in sparse graphs where you don't have as many edges, compared to an adjacency matrix, which takes up more space, V squared, where V is the number of vertices. An adjacency list, if all you want is to know the edges, just iterate, for example, search over all of the edges, and you need to access all of them, it's easier to do with an adjacency list, because I think that makes sense. If we have this structure, we can just start, all right, here's the edge, here's all the edges. If we go to a matrix, we're going to have to iterate over a bunch of things that aren't edges. We're going to, there are things that are stored here that don't exist, if that makes sense. We're leaving empty spaces versus in an adjacency list, we're only storing the meat, the actual connections. Okay, so faster to iterate over all edges, slower to iterate over all edges in a matrix. However, with an adjacency list, looking up a specific edge to see if it exists, for example, can be slow. In a matrix, it's very fast. You can see that on our big O here. To query something, O of 1, constant time for an adjacency matrix. So if I wanted to know, we go back here, is there an edge between A and D? All I have to do is go find that slot, A and D. No, there's not. Is there an edge between B and C? Go to B, C, yes, there is. It's constant time. If we compare that to an adjacency list, actually let's go to letters. If I want to know, is there a connection between A and D? Well, I'm going to have to ask for A first, then I'm going to have to iterate over this. So depending on how many connections there are, how many edges to A, there could be a ton, and I might have to iterate over the entire thing, depending on the number of edges. So I can't know instantly like I did with a matrix. So that's where we get O of V plus E, where V is the number of vertices, E is the number of edges. So the big O itself doesn't matter that much right now. Just know that in general, a matrix takes up more space. When we're talking about sparse data sets, it's not great. It's slower to iterate over every edge, but it is faster to look up a specific edge. Also, some people think the implementation of a matrix can be a little easier. An adjacency list takes up less space, it's faster to iterate over all edges, but it's slower to query for the existence or to check if an edge is in there. So which one are we going to use? Dum, dum, dum. We're going to go with this rainbow, beautiful text, an adjacency list. So excited about it. It's in there 3 times. Why are we going with an adjacency list? Well, mainly because of the space that it takes up and the fact that most of the data in the real world, whether we're talking about social network data, friends, modeling actors who are in movies together, Wikipedia pages, whatever it is, real world data tends to be sparse. So we can have a ton of nodes, lots of vertices, but usually they're not all connected. And that lends itself more to adjacency lists. Remember this chart. Look at any given node on here. It doesn't really have many connections. Like, some of them do, definitely, but there's a lot of nodes that only have one edge, one connection. So for each one of these, whatever the number of nodes is here, the number of vertices, it's going to make a massive matrix. Versus if we're only storing the actual connections using a list, it's a lot easier. And it takes up less space. So because most real-world data looks something like this, even though there's a ton of data here, it's a large set, there aren't very many connections compared to how many there could be. So in a matrix, it works well if your data is jam-packed. If your matrix could be almost full, then you might want to use a matrix. But otherwise, I prefer to use an adjacency list. So that's where we're going. And finally, in the next video, we will set up our code and get started.